So today we're going to get into foam tolerances, and here are our objectives. We'll of course cover straightness, then straightness, flatness, circularity, and cylindricity, in this chapter, which is your unit 6. So first thing we're going to get into is your geometric straightness control. So let's see how we handle this. And this is just showing you a little cartoon, tolerances of forms. And we'll start with the feature, straightness, and of course, see like how he straightens that out. So here is our control frame, feature control frame, telling you about the straightness and tolerance is 0.2. And again, here is your leader line right there. It's showing you the very top surface of your part. And it's showing you the perfectly straight line, You don't have any dimension showing you, there's just a geometric tolerance right there. So we don't have a datum, reference in this feature control frame at all. And that's true to all form tolerances, So in your summary table in Unit 5 lecture, there's a table for form tolerance, and in there the very first one is a straightness, which is a little line. So make sure you consult with that summary table. And there's no dimension, it's just showing you the height of this thing, and this is a tolerance of that height. We're just talking about the straightness of the surface, and given to you the information in the feature control frame, so I know that I am dealing with the surface straightness 0.2, It's my geometric tolerance. Okay. Okay, we're going to use the two little parallel lines right there. See that? And that is the tolerance zone. Okay. So when you see these little two lines, that you know that we are showing the tolerance zone, which is 0.2 for that surface. So the control is dealing with your front view. So your control, applies to only that view. So if you think about all three dimensions, you're gonna have like a 0.6 millimeter for the whole thing. So that's what's saying the straightness control from the front all the way to the back. Because you have a side and the back, you're gonna have like a 0.66 millimeter. So we already knew the straightness tolerance 0.2 is gonna apply to the view. And if you have the straightness in the cross, orientation, and then that's going to be controlled by your size, dimension tolerance, which is 0.6 millimeter. So here just something that you need to know, that we have infinite lines, so let's go back to our mathematics knowledge. So there's an infinite number of surface line elements, and that is going to give you the entire surface. So if you take a look at the surface, you know that there are infinite number of lines in there. So when you do inspection, of course, you're choosing enough lines out of that surface, to check all of your tolerance if they're okay. So surface 0.2, the size, is going to go with the 0.6 with your height. Alright, so the straightness of the line, we're going to continue with this example here. So we have a same surface, but we have two different, these are called the geometric tolerances because they're in the control frame, meaning like this little box right there. They're dealing with the straightness because you can see the symbol, different tolerance value right in there. The only thing that's different is they're in a different orientation, okay? So that's orientation 1 and 2. So you have your front view represent across a horizontal orientation, and left to right, the right side view is going to show a longitudinal horizontal orientation, yeah, front to the back. So you have a two different tolerance, depends on the view, yeah. So this is your right side view, and that's your front view. Right side view is going to go with the 0.1, and the front view is going to go with 0.05. Yeah, so between the two parallel lines for that surface. So here, if you have a trouble looking at the view, yeah, front and your right, then here's a three-dimensional, yeah, pictorial type that you can be able to see where they are. So you can know that this is a 0.5 tolerance from, yeah, and then this one is your right side view, which is your 0.1 tolerance, and that's for your front view. So front view is looking at when you see this, yeah, edges right there. You can see right here, yeah, right side view, of course, this is that and that is this, okay? And you're dealing with this. See that? For the same surface, but you have a two different, yeah, dimension. Here, you will call that a width, and then this one is your depth, yeah? All right, then we get into the rule number 1 for straightness. Rule number 1 is just dealing with your automatic straightness control, and we call that the default, yeah? So when you have like an MMC, so all of your lines are going to be on that feature, yeah? They will have to be perfectly straight, okay? Straightness and flatness is not the same, they're different. So straightness is only like a single line element control, yeah? Flatness is a totally different thing. So again, amount of the tolerance, yeah, that can be permitted. So your variance depends on your tolerance. So that's going to be the amount of the departure from the MMC, yeah, away from it. So surface elements, they gonna still be within that overall size tolerance, yeah. Don't worry about it. Right now you won't get it. You have to look into the diagram, okay. Lower limit of the size tolerance. So that's equal to the full, yeah, extent of the size tolerance. I'll show you this in the diagram so you can see it better. So we have a dimension right here, top and bottom, yeah. Size tolerance, so when you look at it, it's about the 0.5, yeah. You just subtract that. Of course, they're going with a millimeter for this example. And line elements on the entire surface. You got a straight, yeah, with the 0.5 millimeter, yeah, tolerance. So that's all the set, yes. Don't forget the dimension is given to you between the top and the bottom, yeah. So line element across the entire surface gotta go with that. So yes, for that surface. So you start thinking about, oh, where is the surface? Right, surface is a view, yeah. So you're not right now to with the front view, yeah. The next one, again, your straightness of all elements in all direction got a full 0.5 millimeter tolerance zone because it said so here, yeah. And now we're gonna put, see that surface right there, yeah, because that's between the top and bottom, so your surface is going to be right here, yeah. And of course we're using this, yeah, tolerance for that surface, again specific to the view, yeah. All right, and then we are going to combine the rule 1 with the geometric tolerance. So now we're going to bring our control frame right there, and we have a geometric tolerance 0.3 right here, and we're dealing with from top to bottom here, and our tolerances right there, yeah. I mean, here is our two parallel lines, and this is our surface, okay. So this straightness is a control frame is right here. So this geometric tolerance is giving you the allowable tolerance of that straightness, yeah, area on that surface. So now we're gonna draw our little two lines, and that's gonna be 0.3, yes, apart from each other, yeah. And then of course we have a bigger one for this dimension, yeah, which is like a 0.6 away from each other. So you're dealing with the geometric tolerance, and we're dealing with this regular tolerance, yeah. Okay, so here we go. We have a tolerance zone, 0.3 apart, yeah. It's going to flow inside of the rule number 1 limits, which is your limits right here, rule 1, yeah. So 0.3 is from here to here. Yeah, it's closer to the upper limit of your rule number 1 limit here, which is 0.6. See? So how does this go up? Different from the previous slide. Previous slide is the two parallel lines for 0.3 geometric tolerance is in between those two orange lines. Yeah. Of course, any line elements is independent from each other, as long as you're within the limits. Yeah, your limits is again on 0.6 from here to there, and this one is not going down. Yeah, so lower range of your geometric tolerance is given to you. It's just this little line go down. And here we go, let's go up. Now 0.3 is above the limit, which is 0.6 in between the orange lines. This is showing you like how you move away from your MMC, yeah? So it means like the surface changes, yeah, going up. So at that time, of course, you have to do something else, yeah? So let's say tolerance zone is going to float, yeah, within the rule 1 limit. You have a little bit of departure away from MMC. But again, actual thing cannot violate this limit, okay? Zeiss limit is from here to here. So going out, it's not, it's not good, yeah? Okay, then we're gonna bring our gauge blocks and surface plates here. So you see the little diagram, how this is just a sidebar showing you the angle, yeah? So here's the Zeiss and here's the tolerance, but the surface is still between, see? That the Zeiss tolerance. And just showing you sidebar mean you have an angle with the horizontal, meaning like you got elevated by using the gauge blocks, yeah? But you see that the surface is within the limit, see, of 0.6, so therefore the Zeiss tolerance hasn't been violated in this, yeah, example, even if you elevate it. All right, yeah, we have another example here. Yeah, we have two different views. When we're dealing with a cylinder, yeah, so you have a circle and you have a depth right here, so you can see the cylinder or a cone is given to you. And we're dealing with the longitudinal, yeah, lines on that surface. Here is your control frame, and this is your Zeiss limits, yeah, of your diameter. It shows right here. We're dealing with the straightness of the surface, which is on here, yeah. So I start going faster because I believe that you master the views, yeah, of your front and your right, yeah. So if you're struggling with the view, that'll be the end of the world. So your straightness tolerance is showing you here. The pin got to be straight, the tolerance within this 0.04, yeah, and that got to be in this size limit. Oh my gosh. All right, then we bring our lines. We can see like 0.04 is right here. Our surface is right between that zones. And then, of course, since we're dealing with the cylinder, so we bring our centers, yeah, and the axis. And this is your cylindrical pin. Okay. The most important thing is do not violate the Zeiss, yeah, limit. And I'll go with this, and this got to be in this, yeah. Do not violate the Zeiss limit I'll given to you. All right. Then we are going to draw this with a big diagram here, yeah. So here is this, okay, and that can be between, see, this is your 0.4 tolerance zone, which is this guy, right? And here you have your 15, yeah, MMC, which is coming from this maximum, yeah, because we're looking at the external features, so therefore we have to get the 15.00, the upper size limit, okay? So you'll get the most material out of it. But still, that is in between this given 0.04 tolerance range, yeah. So now we have another shape, yeah, here still MMC 15.0, yeah, and here is your part. Look at this little, yeah, for the straightness surface, and we have like a 0.04, yeah, and that was a previous example right there, yeah. Another one, different shape, yeah, variation in your shape right there, and you're gonna have a 0.04 tolerance above here. Your MMC is still 15, yeah. is just showing you a different variation here, and it could also have your barreling. We call it barreling, yeah. In this case, but as long as, of course, as long as you don't violate the overall, size tolerance, you're okay. Okay. Then we'll get into the general rule. Sometimes you can override the general rule, yeah. If you specify the perfect form is not required at your MMC, given MMC, so at that time, you don't have to follow your rule, yeah. So in case of your barreling or wasting, yeah, wasting surface, you can't do your full straightness tolerance, yeah, because again we cannot violate the size limit, yeah. And this is when we do the wasting, wasting mean like a waste right here, yeah. See a little one. If you have a difficulty with the term, it just like look like a waste, and we call it wasting, yeah. Some student made a mistake and they use a wasting. This is not waste, this is waste, okay. Wasting, not waiting. So be careful. It means that, see, because of this going inside, it can go really close to that tolerance zone, yeah. But make sure that you don't violate the size, size tolerance. Barreling, yeah, the same thing here. See, like a little barrel, yeah. I forget to point out about that. But again, of course, see how it's really close to the upper limit, yeah. So make sure that it stay within the upper limit and lower limits. Then you should be okay. All right, then we go into applications. So that's just a little, a flow chart that you can be able to study the straightness. So we're going to begin with this. It's just trying to analyze your drawing, yeah. So when you examine your drawing, and we have to determine, if you actually follow the rules for application of your straightness. We're going to check this way, okay. So that's what this flow chart is about. Now this is just showing you how to, but I'm just running that so you okay. So first, guidelines, yeah. First, we're going to apply to the surface line, yes or no. If you have already applied to the surface line element, yeah, we are going to see if you have applied an appropriate view. First, you do it on surface line. Then check the view, okay? Check the view. Then you're going to check your geometric tolerance, which is inside of the little rectangular box, okay? You will check the geometric tolerance smaller than the size, which is usually show in the front view like a height, okay? And then if that is smaller, you're going to check modifier, your MMC, LMC, yeah? If you use that in your feature control frame. If you use a datum reference in your feature control frame, which is your box, yeah? And then after you check that, you're going to see geometric tolerance, which is a refinement of your indirect GDT controls, meaning like you're just looking at your geometric tolerance, yeah? After you have checked your size limits, check your material, modifiers, and then you check your datum. And then if that's acceptable, everything's good, everything is in, no violation have been occurred to all of the tolerances, then it's kind of acceptable, yeah. So your application is okay, for using this geometric tolerance control for your straightness for that, surface line. All right, unacceptable. You look at it, you check your drawing and you see the surface line. Did you apply to the surface line? You didn't apply to the surface line, so therefore it isn't, acceptable. So what you have to do is fix it, yeah. The next one, if you didn't apply the appropriate view, you've got to fix that, to get the right view. And if your geometric tolerance is not smaller than the size tolerance, it is not acceptable. Yeah, something's wrong. Then you look at your modifiers. Yeah. If your modifiers are used in the feature control frame, that's also something's wrong. Then you look at your datum reference, yeah, and if you use it, then that's also something's wrong. The geometric tolerance, yeah, and you check, and if there is no geometric tolerance for your GDT controls, then it is not acceptable, yeah. Because if you apply the geometric tolerance, it's got to be a refinement, yeah, refinement of any other geometric tolerance that indirectly control your straightness. So combined, no, and you go here, yeah. Modifier, the datum, if it's yes, unacceptable, no, gonna go straight to acceptable, yeah, because you don't really need this anyway, because we're dealing with the geometric tolerance and size limits, yeah, for the straightness. Okay. Then we'll get into the second handout, yeah, the straightness of the feature. Okay, so we go into a little quiz, and that's, I think, in your book, problem number 49. I want you to do this by yourself, yeah, attempt it. Of course, I give you your hints right here, yeah, your answers right there, but this is your homework. You can choose this problem. I only want you to do 3, yeah, so I know you at least do 3 in it. Alright, so then we'll go into straightness, and we're going to apply to the size, feature size, yeah. So form control, this is outside real world, and you can see a dial indicator right here. It's just equipment measurement, yeah, for measurement in your metrology. So this type of setup is often used in the process of verifying form, yeah, during the production parts. So this is how you measure, yeah, how you measure the form in the application outside. We use the gauges, of course. These are your dial indicators, so review of your metrology, yeah. We're going to use it to measure the variation from the dimensional limits, yeah. Again, on the form tolerance, you have different types of tolerance. We're getting into the very first one, which is your form. In form, we're getting into the straightness, yeah. So here, this is called a probe, yeah, like your electronic lab. So this is your spheroid tip probes. You have different size and flexibility. Gauges, yeah. We have V blocks, yeah. We use them, yeah, to create the cylindrical parts in your inspection or also manufacturing processes, yeah. You will see them all the time. This is a very well-known company, yeah, Itutoyo, Japanese. Okay, gauges, yeah. And so this is your surface plate. It is very important in process, manufacturing process, also inspection, yeah. Make sure everything is in the right specification and tolerance. It is made from your solid granite, and they vary in size and also thickness. Of course, they are used as a datum plane simulator. The next one that you can see outside, and these are your, again, gauges, yeah. These are just the tools, yeah, that we use in inspection process to make sure that they're in the acceptable tolerance zones. Okay, straightness characteristic. So you have your geometry control for the straightness, and we're going to apply that. Since you're dealing with the straightness, we're going to apply that to the line, okay? Element means it's just a line. Don't worry about these words, just a line. And of course, that line is on a surface because you're dealing with the straightness of a surface. But when you deal with that, we usually use a line on that surface, okay, to apply the tolerance on it. Or we can also use a width or diameter or thickness, yeah, thickness, your depth, yeah, of the object to study the straightness on it. So we have 3 things going on, dealing with the tolerance zone for straightness, yeah. So if we apply to a feature on the part, yeah, if you apply a feature on the part, or if you apply to the size of it, yeah, feature of size. I know that a lot of the students have an issue understanding between the feature on the part and the feature of size. Yeah, this is dealing with your dimensions, by the way. That's dealing with your physical thing, yeah? So be careful. It's just a wording. Okay, so now let's get into how to apply it to the feature of size. Just read this, yeah, and I'll show you each example. If I read it, you're not going to get it. The very first one. So here is two views, yeah, and you have your size limit right there, and you have your control, yes, which is your control frame here. And that is again called the feature control frame because it is dealing with the feature, yeah. So here again, the student have an issue understanding the feature and feature of size, okay, because they look very similar, okay. So make sure you get that distinction between the feature and the feature of size. Yeah, here on this side, so that's your left, okay. This control we call it feature, yeah. So when you notice your tolerance zone, don't feel bad when you read a resulting tolerance zone. All you have to know is like we're talking about like this surface, tolerance zone, geometric tolerance is we're always dealing with here, that's where your two little lines with this sides is going to be right in there, But here we're dealing with the surface feature, so therefore this side is a feature, yes. And when you look at it here carefully, see, it's not showing you the surface. Right now it's showing you, see this limit right there? See? So that's a major difference. So that geometry, all right, tolerance has a, like, remember your bonus tolerance? Yeah, we play with away from MC, yeah, and 10.8, right? And also, of course, it depends on whether internal or external features. So anyways, right now I'm just showing you right here on this with a particular, limits right there. So that's, we call that the size, the diameter size limit right there. So in this case, you know that you are dealing with the feature of size, okay? Feature of size, feature, and feature of size. So it depends on where your arrow is showing, yeah. So sometimes you have a confusion because you're seeing this and you thought like, oh, that could be the feature of size. No, because of the control. Yeah, the control is not right here. The control is on this side. See how the control is, see, like together with the limit, size limit. Here, size limit is independently, displaying on this side without the control. So this one feature and that one a feature of size. Okay, you have to get this. All right, next one, going into this. All right, then we get into our fundamental rule, for your automatic straightness control. So that's just trying to say, like, if you combine your first fundamental rule with your standard, coordinate dimensioning or tolerance, and you're gonna have just a limited, straightness control over that center plane or the axis of your feature size, feature of size. So in that condition, when you have a part and that part is at MMC, okay, your max of material condition, then your center plane or axis, okay, will have to be perfectly straight. It's got to be straight. That's all it said. Right now you won't understand this, by the way. You have to look into the diagram. I told you several times. But just read it and calm down, and don't go so much into it and trying to memorize. You can never memorize any of it. All our questions will not be asking you to memorize everything, okay? Pretty straightforward, so for you to be able to recognize, oh, this one, that one. So when you draw it, you usually use application, either SolidWorks or AutoCAD or something, and you can pay attention to these things, okay? It's impossible to us, as students, everything to remember by heart. It can't. Probably in a long time ago, maybe older professor might do it to torture you, but not anymore. So if you come away from your maximum material condition, then you have your variation, because you can keep the perfectly straight, what it's supposed to be. So at that time, you're gonna have your you're gonna go from the MMC little by little, okay. So your variation, okay, gotta come out equal to the amount of the departure from the MMC, and that's completely permitted. Of course, you have to change your tolerance. I'll show you later. Now, any variation in the center. So if you have any variation in the center plane or axis, would be the result of your surface elements. Yeah, elements meaning it's just a drawing. Yeah, drawing elements for your surface. Their lines, right, interacting with their within the tolerance limit, instead of just a specific control over the center plane or axis. Yeah, so there's more going on the elements on the surface. You can get it right now. Just read it. Don't get frustrated. Okay, so let's just see with the diagram. So rule number one, your default is the straightness control. So here you can see two views. Yeah, you have right here. As soon as you see this, you know that you're dealing with the limits. Yeah, Zeiss limit. When you look at the Zeiss limit, yes, we have upper max, which is 10.6, and then lower, yeah, min is your 10.0. So what it's saying is, if you go MMC, then we're gonna have like a perfect Zeiss, and then your cylinder form, right? Because we're dealing with a pin anyway, it's gonna be so perfect because you're dealing with the 10.6 maximum, and you have your external part right there. So therefore, for most material to be left, you have to choose the upper limit. So when we say the perfect size, meaning like it's answer to the maximum material control, your value answer to the MMC right there. So when your pin diameter go down, from the max going smaller and smaller, in your line elements on that surface, right? Meaning like we are moving away from 10.6 and going down and going towards 10.0. So 10.0 is your LMC, your least material condition. So moving away from there, coming down little by little, towards 10.0. But it's still, within the Zeiss tolerance limit. So if this surface is going down, either it's gonna bow or deform, right? It won't be like a perfectly straight surface anymore. That's what it's saying. The variation mean it's not perfect straight. It's because the value is reducing from the max material. Meaning like physically your materials are losing from the top of the surface. Going down. Okay, so straightness control, now we draw it really big so you can see what's going on here. So you can see the little band. Of course, with the naked eye, you can see that. You will see like always a straight surface. But when you go into there and make it bigger, then you can be able to see, how there's little tiny variation going on between that size range right there. So pin diameter is smaller, than your MMC, but still is within the size tolerance right there. So that's your rule number one. They call it for straightness. So rule number one is a boundary is here, is your mating envelope. So when it's got affected, so your axis, right in here, see how it curved a little bit, meaning like it got affected because of that variation on the surface, because you're moving away from the 10.6, and going down. And of course, this one is moving away from 10.6 and going inside. So you got band, in here in this example. Okay. Of course, we go all the way down to the smallest diameter, which is our limit at the limit, 10.0. So when you get all the way to the lower limit of your size, range right there, limits here, then see like how your axis get curved. Of course you can again won't see that 0.6 difference in there, but if you go all the way to the end to 10.0, we will call like that. The center axis is kind of like band. So a bowl. Not a perfect cylindrical axis anymore. Okay, then we'll get into feature of size, RFS again, that's your regardless of feature size, not your MMC or LMC, and let's see how it goes. Here, your feature control frame is associated, not the surface feature. This is a feature of size, so therefore we use a regardless of feature of size. So here is your limit, and here is your diameter of that, hole right there, and then that's your geometric tolerance, Again, the control is going to be on the axis of that part. Yeah. Why? Because it's easy, because in the example you always see the axis, so you know the control is right on there because of this face. Yeah. Of course, now we're dealing with the feature of size because we have size limit and also the geometry tolerance right here written there for you, and we are going to override the rule 1. Yeah. Why? Because we have a geometric tolerance is going to be applied to the feature of size, so we don't do the rule 1. Rule 1 is strictly for the regular feature. Yeah. We can also calculate the virtual condition because you have all the numbers here. So if you calculate it, you're going to get the mating part envelope of that pin is equal to your max MMC of the pin, and you're gonna add 0.2 to it, so you will have like 12.6 and 2 is 8. 12.8 millimeter. Okay, then regardless of feature size, your feature axis straightness, I'm going to maintain with that is because we're applying to the feature of size here with your geometric tolerance in this example. And you're gonna go and here is your 0.2 geometric tolerance right in there, regardless of your feature of size, it's just stay there. And then we have our smallest true cylinder in contact with the high points of the surface, which is coming out from this range. And you can see there's a little arrow right there showing you 12.0. See, careful. So 12.6, right there showing you this blue zones right there. So we have 2 zones, this and then this little zones right in there, which is encompassing this axis of that cylinder pin. So max diameter is 12.8, including this tolerance. Okay, this is what we're talking about, because you have to consider both of them at the same time. Therefore you add them up for max. And of course you override the rule number 1. Your virtual condition, you're gonna add it up 12.6 plus 0.2, so you get 12.8 for that RFS. Okay, and then this is your table again, going away from like 12.6 all the way down to 12.0. And we're gonna go each one of them 0.2 down. So what are we doing? We are applying, the tolerance, which is this guy, straightness tolerance. That's what it's saying, straightness tolerance. We're gonna apply to the feature because that's your feature size. 0.2 each. Each unit you go towards your LMS. Physically, of course, that's bending, or bowing. This is just showing you that we have to identify the material condition modifier in your control frame when it's important to modify the straightness control to a condition. So you must mention the MMC in your control frame. So let's take a look at that. So see now, look at that. So this is what we're talking about. This is your control frame dealing with the straightness. Here is your geometric tolerance, and here is your material a condition modifier, which is your MMC in this case for you. It's right in there so that you know what to do. So again, the size 12.0 to 12.6 virtual condition, your max plus your geometric tolerance. Very easy to calculate. This is showing you without the bonus tolerance. You will have 12.6 for max. And then 0.2 without the bonus, so you will get the total diameter tolerance zone is 0.2. Doesn't change. Okay. Of course, if you got like a bonus tolerance and you add each one of them, you will get a combine right here on this side. Okay, now we move away. We move away. Tolerance zone still there. Your virtual condition, yes. 12.8 at max. So in here we've got a 0.2 bonus tolerance added to our regular one, and you will get a total 0.4 for this case. We move away from 12.6 to 12.4, so that's 2 units away. Okay, so therefore you have 0.4, meaning like you don't have a perfect straightness. You're going down from the max towards 12.0. Going down from 12.6 to 12.2, and we have bonuses 0.4. Because they're 2 units down, so the combined is 0.6 now. Go down all the way to 12. Next 0.2, we're doing 3 times, so therefore 0.2 times 3 is 0.6 added, and you get 0.8 for the combined total tolerance. Okay, so what do we have to do with this bonus stuff? Because they give you the flexibility for manufacturing. So when you draw, you gotta add that. Why? Because manufacturers, you're dealing with the physical stuff. So even though you're drilling or something, you make a lot of mistakes. So one mistake is gonna rip off all the material around it. So that's the reason why we need this bonus tolerance when we deal with the feature size. Feature of size. So that way, if you don't like defect it, when you do the machining, then you save a lot of money. If you get a lot of defect on it and make mistakes when you are machining, of course, to repair all of that or replace, it just take a lot of time, and time is money, of course, in manufacturing, because you want your product to go on, streamline it without or minimum amount of mistakes. So the tolerance is very important, because that's where they have to play. Your Six Sigma, the same thing. The Six Sigma has a 6, right? All the way in Sigma, which is your same is very much similar to the tolerance, by the way. So you give like a real big 6. So that way a lot of the production can happen in between that range. So anyways, let's go to the next. So here we can read it by now. You have your here is your control frame. Here is your dimension right there, size limit, and control frame, your geometric tolerance right there with your material condition modifier at MMC. So you have your receiver gauge. You have your mating, of course, boundary limits, and you have also your virtual. This is where VC is a virtual condition given to you. So this is this. That is this plus that. Okay, so you know how to read them and how to write them, right? Pretty easy. Of course, 12.8 is bigger than 12.6, so when you draw, 12.6 got to be inside, of this. So this dimension with your extension line, another extension line for this dimension. Very easy to see that. Of course, I'm not going to torture you to draw it on your CAD application of some sort, but you should be able to draw this. Okay. So if we deal with the pin diameter, this is your pin, and that diameter, we're going to have a perfectly straight, because we're dealing with the straightness right here, dealing with the diameter of some sort, so you know that it is some form of cylinder based on this example given to you. Your gauge is going to be at the virtual condition. Gauge is something that you measure that against, especially in the inspection, to see if your tolerances are correct. Okay, now we're going to move away. So MMC, your gauge is going to accept. You have like about 0.2, of course, a variation. Thus it said it's so here. Then we go all the way to the LMC. LMC is a 12.0. Gauge is going to accept. It's got to be a 0.8 variation, because you're going down. From 12.6 all the way to 12.0. So 0.8 is you can be able to get it by subtracting 12.8 minus 12.0, so you have a difference of 0.8 variation in your straightness. Alright, So we go 1 and then 2. Here's a diagram. It's a little bit complicated. And here's your 3 is this diagram. So don't get confused. So we started out with your, so perfectly straight at MCC. Coming down, we have about the 0.2 variation at the axis is a control. And then we're going to go down, all the way to 12.0, which is your LMC. So at that time, we have 0.8 variation in the straightness. Okay. Of course, outside physically, it is this is giving you the exaggerated diagram here. Of course, outside you can see these differences or variation in naked eye. So this is just a diagram. We show that how this 0.8 is going into like a little arc or bow, and your axes get affected in there. Okay, concept that you have to remember, we deal with the rule, surface is okay, when you deal with the size, limit, and then sometimes you have to override it. Meaning like when you use your geometric tolerance, to your feature of size, rule number 1 gonna override it, Also your VC is affected, yes. Why? Because we are considering this geometric tolerance over the size limits. And we show you from going from MMC to LMC, and how each geometric tolerance is added up, to each small unit going down, from MMC to LMC. And you have your total, tolerance is the one that you want to use instead of applying the rule 1. Why do we do that? It's good for your manufacturing, and save a lot of money. Okay. All right, unit basis. This is just for you to read. The specifications are very important because you want to reduce the variation, amount of variation. Because here you're dealing with the straightness, so we are dealing with the longitudinal distance, your lines. And we definitely need to control the curvature and deformation, but that's against the straightness, So if you just want to limit the tolerance zone size, and every time your distance is extended, you have accumulation of tolerance, and you still need to account for that. So straightness, you will apply, you will apply that on a unit, unit basis. Unit basis means unit of control straightness per length basis. But of course, when you apply the straightness in a unit basis, then you gotta be careful to deal with the maximum limit, because the maximum limit got to be still, within the limit of your variation, allow the variation. So that's usually come from the perfect straightness. I mean, like you can't have a perfect straightness when you have variation, because it will be away from that ideal situation. That is what it say. In real situation is you can't get perfect straightness. It will always stay within that tolerance zone. It's just like telling you again the same thing, but the real thing is pretty easy. Student get incredible amount of I think wording and terms is confuse you, and you might have trouble to relate the terms to the physical thing outside. Outside I just want you to for this level, and just try to remember you're dealing with the two different numbers. One is the size limits, and the other one is your tolerance. And we play with that. We have a two limits, the upper and lower, and a lot of things can happen in between that two. When it happens, you have to account for that variation by using the geometric tolerance. That's about it. If you get about that much, I'm pretty okay. All right. So here we're dealing with this time our pin. This is a shell because it's a little bit longer, And straightness, of course, you can see this little symbol. You have your axis because we're dealing with a shell. So there's a circle and you have your two views right there. We have a cylindrical tolerance zone given to you here. Size limit right there. Geometric tolerance 0.2. Yes. So you can vary, you cannot vary more than 0.2 millimeter, yeah, per any 20 millimeter length, yeah. Because it said it so, where does this 20 millimeter come from here? It said it's 0.2 per every 20 millimeter length, yeah. You cannot vary more than 0.2 millimeter for 20 millimeter length, okay? A little bit different way of writing, be careful. And there is no maximum limit, yeah, maximum, there's nothing, material condition isn't given there for you, just straight. So since you don't have a max, so sometimes you're gonna go like, you know, a huge error like that. So you gotta be careful with this type of tolerancing. Okay, we're gonna first take a look at it. Yeah, we will see the extreme possibility of the variation if, that can be able to apply to this example. So here we go. So we have total, we have no total variation. So there is no control, yeah, to limit your tolerance accumulation. And we're going in the same direction. So you go like 20, 40, 60, 80, yeah? So every 20 you can go 0.2, so 40.4 and 60.6, yeah? So which is this little guy is telling you about, see? So every 20 millimeter. It doesn't give you the max at all, so therefore you can go all the way to 80 because you add it up, yeah? Another 0.2 to 0.6, yes? All right. Here now we have a total, yeah. So right now you have a composite right there. See, composite feature control frame is there for you with the size limit right there, yeah. So it tells you the overall, yeah, the medium line, same thing. So you have like a 0.2 over 20 millimeter, yeah. And then there is another unit, right? Another value given to you, which is 0.5, yeah. So that's your cylindrical tolerance, 0.5, all right, total in any 20 millimeter length. Yeah, it's got to go to here. So you can't go anything more than 0.2 millimeter outer straightness, yeah, for that excess of that part, because it gives you the tolerance, another tolerance that you need to pay attention to. So let's go and take a look at it. Yeah, so here is our variation. We're going to go all the way to, yeah, from here to here, 60, and this is of course 0.5, this one, yeah. And we have our sides, which is a 14.5 outer boundary. So if you miss it, it's right here, yeah, 14.0, 13.87, you can go up to 0.5, yeah, beyond that. So that's what you are seeing, 14.5 over here, to your outer boundary max. And of course, your composite, yeah, feature control frame says 0.5, you can go, yeah. Don't confuse this 0.5 and that 0.5, yeah. This is your straightness, your axis control right there, yeah. The straightness tolerance control is a cylinder, so therefore we put it like right at the axis where you measure your cylinder. So that's a 0.5 millimeter because it said it's so here, diameter, see? That's why we measure from here. Okay, and of course here we have our first 20, which is this. That's a 0.2, yeah, diameter tolerance zone in any 20 millimeter. So we will go in there, yeah, it's just right there, and that's just showing you the variation that it can go along this axis, yeah. And you cannot go anything beyond that, yes, tolerance zone right there, because we already fixed it, yeah. 0.5 is your max right here, so that's got to be inside of it. But if you go like 40, it's going to shoot out to 0.4. Okay, then 0.2 diameter tolerance zone in any 20 millimeter, yeah, of length. So this is kind of like a really big and large view for you, yeah. You might want to take a little bit of time to look at it. I provided your PDF handout right there, yeah. You can get it just by listening to lecture one time. Yeah, you have to back up 3 hours for every hour of lecture. Yeah, you must do that in order for you to actually get it. So here we go. So we're gonna look at this, yeah, drawing, your interpretation. 14 max, 13.87 minimum. You can go 0.5, yeah, and composite control a frame right here, 0.1 to your tolerance every 20 millimeter. So that's where we start drawing 0.2 diameter tolerance zone in any 20 millimeter length. Show that. Okay, first dimension right there. Second dimension right here. Yeah, so that's your size dimension right there, 13.87 to 14. Yeah, and this is just a length that's for your cylinder. This is your right side view, so it's your depth, right, going in there like that. And then of course that's on this side, which is your front view right there. You can see only a circle and that diameter, because we're dealing with the diameter right here. You can see this little symbol. That's a 14.5, yeah, outer boundary. Yes, that's because you can go all the way to 14.5, yeah, with your tolerance given to you. Okay. Oops. All right, sometimes straightness can be controlled, yeah, by different geometric tolerances. You have like angularity, parallelism, and then your perpendicularity, profile, position tolerances, your runout, yeah. So the axis or median planes of any of your features or designs, the straightness, yeah, can be influenced and controlled by these geometric tolerances at the same time. Yeah, that's what it's saying. So in that case, yeah, if you have like indirect control by these geometric tolerances over straightness, then that straightness got to be refinement, yeah, of each of other tolerances. Meaning like you have to pay attention, yeah, when you have other stuff, you account for these extra tolerances affecting the straightness. You can't just use a perfect straightness, yeah, that's what it's saying. Okay, it's not a big deal. Let's go into application. Yeah, straightness applied to a feature of size. So here is our flowchart diagram to examine everything is all right or not. So let's start with that. So first, you're gonna check, yeah, feature of size. Do you apply that? If you apply that, we're gonna go second step. Or do we have appropriate view associated? Yeah, plane or axis. If you have it, then we're going to take a look at our tolerance. Yeah, the refinement of the indirect GTP, any controls over it on your straightness. So that's what we're dealing with right now in this case. And if that's yes, we will look at our datum reference. Yeah, if that's no, it is acceptable. Yeah, so this is the decision I'm making on flowchart for you. Yeah, in order for you to reach to the correct application of your straightness in your drawings. So if no, if you didn't apply, you will apply to the feature of the size. That's not right, so fix it. If you didn't apply to the appropriate view, yeah, associated with the plane or axis, fix it. Then you're gonna look at your geometric tolerance for the refinement, right? If there is other GDT controls over it. If there is no control over it, then that's unacceptable, yeah? Why? Because other geometric tolerances, you always have it in your parts, yeah? Of course, our example in the lecture don't have it, but outside you always have it. So other geometric tolerances, they indirectly affect, yeah, the straightness of the axis or the center plane, yeah, of your xi feature. So straightness, when you apply to the xis or feature of xis, is going to be, yeah, it must be a refinement of these indirect control. So you have to go down and say, oh, it's unacceptable, then correct it, yeah, then you will take a look at your datum. If datum reference, yeah, is in the feature control frame, then it's unacceptable. Why? Because datums are never referenced, yeah, in the feature control frame, right? We didn't see it. Your box, right? Your little feature control frame always have like just two boxes in there. Yeah, datum box is always off anyway, right? You have only two columns in there in one row. So if you got it, then it's wrong. So it's unacceptable, yeah. Because the form control always relate to their own, right? True geometric counterpart. All right, so this is a big picture of your yes and no's decision making. Yeah, I want you to read it and study it. Of course, we're not asking you all of it by heart. If you pay attention, it's okay. All right, straightness of a feature of size. This is just a little your textbook problem. I think number 50. Yeah. So again, that's your homework. You have to do your assignment in class. And the answer is right here. And so I'm not going to go over that. So for you to read it. Okay, so we cover everything. Yeah. We talk about the axis control, the geometric tolerance, when you apply it, and we always apply it to the line element or feature and straightness. And then we talked about the straightness, geometric control got to be associated with the size dimension. We do it again and again, yeah. Your size limits, modifier, your MMC, yes. You can find that in your given in your feature control frame, right? Associating with your geometric tolerance, yeah. So that's very important when you deal with the size feature, yeah, in straightness, yeah. Your straightness control also got to be, yeah. So when you pay attention, yeah, the first three I just read it for you, yeah. So the very first one, yeah, it's not true, yeah, it's not true, it's false, because you have to understand, yeah, the relationship between this geometric tolerance and feature of size, yeah. So I want you to, yes, go back to that too, and to pay attention the feature and also the feature of size, yeah, and your axis control. Okay, there are two different things. The second one is true, yeah, because your straightness geometry control must be, again, must be associated with your size dimension. Okay, the third one isn't true because sometimes we don't use modifiers, right? It's off and empty anyway, right? In some of the examples that we do. So these are the little things that you gotta do in your homework, yeah. So make sure you do that. I did the first three for you. All right, that's it for the part one, and we will get into part two.